Hi everyone, welcome back. So this is going to be a lesson for linear algebra about properties of determinants. And we're basically going to pick up where we left off last time. We had established a lot of things about determinants, but there were still some kind of open questions that we need to address about how does row reduction affect determinants. And we also want to see what other properties we can come up with. So let's go ahead and see what we can do. All right, properties of determinants. I want to start by reminding you of what we talked about last time in the previous lesson. Just a real quick recap. We had the definition of determinant of A for an n by n matrix A. And we learned how to compute determinants. For the 1 by 1 case, that was pretty simple. The 2 by 2 case, that has a shortcut. Technically, you don't have to use the shortcut. You could use the definition of the determinant for the 2 by 2 case if you wanted. And the 3 by 3 case, you could either use the definition, or you could use theorem 1, or you could use a special trick that we did at the end of the lesson. And in general, the n by n case. And we did some 4 by 4 determinants, and you could apply those same methods for 5 by 5 or anything larger as well, as long as it's a square matrix. I want to remind you what Theorem 2 said, because it might show up today. Theorem 1 might show up today also, but Theorem 2 said if A is triangular. I mean, we say that a matrix is square, and we also say that it's triangular. I hope you know what we mean by that. Saying that a matrix is square means that it's an n by n matrix. Saying that it's triangular means that it represents a triangular system, so it has zeros in particular spots. But the theorem basically said that the determinant of A would equal the product of the diagonal entries. And that means the entries along the main diagonal. You multiply all of them. If it's 3 by 3, then you have 3 diagonal entries to multiply, etc. All right, so that's where we left off, and then we kind of left off with a question, which was, how does row reduction affect the determinant of a matrix? And I kind of discussed this question briefly, and I didn't give you the answer yet. That's what we need to figure out. But the reason why I think this question comes up is because of Theorem 2, right? If you had a matrix that is not a triangular matrix, you might think to yourself, oh, well, I could do row reduction and turn that into something that's triangular when it's in row echelon form, and then maybe I could apply Theorem 2. Is it okay to do that, or does row reduction change the determinant? So what we're going to do is we're going to figure out the answer to this question, and for now, I'd like us to focus on the 2 by 2 case. So we'll keep things small for now, and we'll generalize the result for n by n. But for now, if you have a 2 by 2 matrix, you know that when we say row reduction, you know that there are 3 different row reduction steps that we're allowed to do. And let's look at each of them and see if they affect the determinant or not. So let's start by checking what happens to a matrix when you interchange rows. Like if I interchanged rows from a matrix, does that change its determinant? So in the 2 by 2 case, there's only one way to interchange rows. You would swap row 1 and 2, so you would get C, D, A, B. Do you think this changes the determinant? Let's find out. Let's call this first matrix A, and let's call this second matrix B. Now, I want to be clear to you. I want to be clear about something. A is, assuming that A, B, C, D are, I don't know, random numbers or something, A is not typically equal to B. They are not equal matrices. I mean, they could be if A, B, C, D, and, if A and B and was equal to C and D, but that usually doesn't happen, right? If this was like 1, 2, 3, 4, you interchange rows, these matrices are no longer equal to each other. We say that they are row equivalent, and that's not the same as being equal. Okay? Well, we could figure out the determinant of each of these. The determinant of A would be AD minus BC. And what would the determinant of B be? The determinant of B be? Well, we'd multiply C times B minus D times A. I'm going to write it like this. BC minus AD. Are these equal to each other? No, right? They're not. In general, they're not. We could say that what we got actually looks like the negative of the original determinant. We could say that this is, in fact, negative AD minus BC. So interchanging rows changed the determinant from whatever it equaled to now it is the negative of that. So let's write that as a result. The determinant of B is equal to negative the determinant of A. I'm going to circle this. So there are 3 different types of row operations, and we just checked one of them, and it seems like it does affect the determinant. It changes the determinant in this way. Let's check the other ones, though. Maybe, what about the other 2? Maybe they do the same thing, or maybe they do something else. Let's find out. What happens if we multiply a row by a constant? Because that's another thing that we're allowed to do. So again, let's suppose that we start with a typical 2 by 2 matrix, A, B, C, D, which I'm going to call this the matrix A. And then we're going to multiply a row by a constant. Should we do this to row 1 or row 2? I think this might be kind of a without loss of generality situation where we could do this to either one. But let's try it on row 1, and then we'll maybe do it on row 2 also, just to see if we get the same result or not. I'm going to call the constant K, because we're already using the letter C. So there we go. I multiplied a row by a constant, and I get a new matrix B that is row equivalent to A. But did it change the determinant? The determinant of A is AD minus BC. What is the determinant of B? We could say it's KAD minus KBC. Does that look like that's the same to you? No, probably different, right? I mean, it depends what K is. But we multiply rows by a non-zero constant. It's probably not going to be K equals 1, because why would we multiply a row by 1? So we're multiplying by something that's not 0 and it's not 1. And it looks like we probably did change the determinant. In fact, we could factor out K and write it this way. And you can see exactly how much we changed the determinant by. There's the original, and now it's scaled up by K. Well, let's write that as a result. The determinant of B, after we multiplied a row by a constant, is K times the determinant of A. So whatever constant you multiplied a row by, you multiplied the determinant by that. I said we would do this on the other row. I suspect that we will probably get the same result, but let's check it because, we want to be thorough. So let's say we changed to the matrix B that looks like this. I'm still going to call it the matrix B. All right, so what's the determinant of this matrix? Determinant of B equals A. What do we want to say? AKD minus BKC. Well, this also equals what we found above. I'll put a little check mark next to it. Same result that we got above. So, same thing. If you multiply either row by a constant, it has the effect of scaling up or scaling down the determinant by that constant. What do you think? So far, I feel like it's not looking good. So far, I feel like these row reduction steps are changing the determinant. And you know that when we start with a square matrix and maybe we do a bunch of row reduction steps, what if we do like 6 row reduction steps and each one of those steps is changing the determinant? It seems like by the time you get to the row echelon form, the determinant might have changed a lot. Maybe. But is it really changing a lot? I mean, I guess this would just be flipping the sign back and forth every time you interchange rows. You flip to negative, you flip to positive, you flip to negative. This would multiply by a constant. Okay, so that's actually changing in a significant way. Let's look at the third type of row operation. And the third type of row operation is one of the most powerful ones. This is when you add a multiple of one row to another. We need to see, how does this affect the determinant? So I would like you to try this. I'd like you to try to pause the video, do this kind of reasoning that we've been doing above, see what you can find out. All right, so did you pause the video and try that? Did you figure out how does it change the determinant? Does it change the determinant? Well, I'll write it out the way I've been doing it, where we have some generic 2x2 matrix A. And, well, what are we going to do? We need to add a multiple of one row to another. Let's add a multiple of, here's what I'll write it. We're going to add k times row 2 to row 1. Let's try this first. I mean, we either need to add a multiple of row 1 to 2 or 2 to 1. Those are the only two choices. I chose one of them to start with. So A plus a multiple of C, let's call it KC. And then this will be B plus a multiple of D, let's call it KD. And then C and D, that row is unchanged. We call this new matrix B. And we're going to figure out, how does the determinant change? The original determinant was AD minus BC. The determinant of the new matrix is A plus KCD minus B plus KDC. Looks pretty different, right? Let's distribute, expand, see if any of these terms combine. So I guess this is AD plus, let's write these in order, CDK minus BC minus KDC could be written as CDK. Hey, look at this. Look what we got. CDKs cancel. So this is AD minus BC. Finally, we actually got the same result. The determinant of A equals the determinant of B. And maybe that's kind of surprising because the other two types of row reduction steps changed the determinant. Out of all three steps, I usually think of this one as maybe the most important, and it actually doesn't change the determinant. Now, I only did adding one row to another in one way. The other way is if you add a multiple of something to, multiple of row 1 gets added to row 2. You could check that also. I'm just going to tell you that performing that operation on the other row has the same result. So that's great. Now we're going to generalize this to a theorem, and this is theorem 3. Let's summarize the 3 results that we just found. Start by saying let A be any square matrix. Because at this point in the course, we're mostly interested in square matrices. Remember, everything in this section is focusing on square matrices because determinants are only defined for square matrices. All right. Part A, I might not be writing these in the same order that we did them, but we'll get all three of them. If a multiple of one row of A is added to another row to produce a matrix B, then the determinant of B is equal to the determinant of A. That's part A of the theorem. I'm circling this. That's what we wrote above. I just am writing it in the other order now. I'm writing determinant B equals instead of determinant A equals. Part B, if two rows of A are interchanged to produce B, then the determinant of B is equal to negative of the determinant of A. I'm going to circle that. And part C, if one row of A is multiplied by K to produce B, then the determinant of B is K times the determinant of A. So this theorem summarizes how row reduction affects determinants. And something that I want to point out to you is that this theorem starts out saying, let A be any square matrix. What we did above, the work that we did above, basically proves theorem 3 for the 2 by 2 case only. And yeah, I'm not really proving it for the more general n by n case, although you could try to do that. It would be, yeah, a generalization of the work that we did. But I think that the 2 by 2 case is good enough for us for now, for the sake of time. And, you know, it was easy to illustrate in the 2 by 2 case. Now, if we accept that this actually works in the n by n case, I'll show you how this could help us solve a problem. I'll do this one for us. Let's say we want to find the determinant of A, and we're going to be given a 4 by 4 matrix. A is equal to 1, 2, 0, 3, negative 1, 1, 3, 6, negative 1, negative 2, negative 4, 5, 2, 4, 0, 5. Now, you know there's a couple of ways we could find this determinant. You know we could use the definition from last time, or we could use theorem 1 from last time and do cofactor expansion across any row or column of our choice. We would probably choose column 3 because it has the most zeros. We could do that. But I want to show you how theorem 3 gives us a shortcut. All right, I see some row reduction that we could do. And it turns out, I'm going to not show every little row reduction step, but it turns out that this matrix is set up in a very convenient way, where if we add multiples of row 1 to the other rows, I'm doing kind of 3 steps at once, I guess, because I'm going to add a multiple of row 1 to row 2, 3, and 4. So row 1 stays the same. You know, in row reduction, what would I do? I would add 1 times row 1 to row 2. That's going to get me 0, 3, 3, 9. And then I would add 1 times row 1 gets added to row 3. See what's going to happen here? 0, 0, negative 4, 8. And then I would add negative 2 times row 1 gets added to row 4. The 2 becomes a 0. The 4 becomes a 0. That's a 0. That's -1. So, yeah, this matrix was set up very conveniently because by adding multiples of row 1 to other rows, we got it into row echelon form. And I want to tell you that the determinant of A, and I want to be clear here, I'm talking about the determinant of A, the original matrix, I'm not talking about the determinant of that. I'm talking about the determinant of A, which is what we're trying to find. What does Theorem 2 say? Theorem 2 says if it's a triangular matrix, you multiply these. What does Theorem 3 say? It says when you add a multiple of a row to another row, it does not change the determinant. And that's the only kind of row reduction step I did. I didn't interchange any rows. I didn't multiply a row by a constant k. I only did this type of row operation. So the determinant of my row reduced matrix is going to be the determinant of A. And since this is triangular, I can just do 1 times 3 times -4 times -1. I multiply those all out and I get 12. So in this case, that's the determinant of both of these matrices, and they're equal to each other because that's the only type of row reduction step that I did. I didn't use the other two types of steps. So admittedly, this matrix was set up to be kind of convenient. And you might wonder, like, well, does that really help us in general, though? Because it seems like when we do row reduction, we usually have to use some of the other steps. Interchange rows, multiply a row by a constant. I see a 3, 3, 9, and I'm thinking I could multiply this row by a constant to simplify it further. But I don't need to. My goal was to get this into triangular form so that I could apply Theorem 2. All right, let's get a fresh sheet of paper. So a few remarks about this. In the previous example, we reduced the matrix A to some new matrix, which we could think of as B, where B is in row echelon form. By the way, it's not in reduced row echelon form. There's row echelon form, which is what we have. It's not reduced row echelon form, though. That's okay. So that's my first remark. And I just said it seems like when we do row reduction, it seems like we use some of those other steps. And I'm going to tell you a fact that I don't think we've said in this course. It's something that we probably could have said earlier, but we didn't really need it until now. Fact: we can always do this without multiplying any rows by constants. Is that surprising? So let me be clear about what I'm saying in this fact. I'm saying that you can always reduce to row echelon form. I'm not making the claim that you can get it into reduced row echelon form. I'm only claiming that you could get it to row echelon form without multiplying any rows by constants. So when we say that there are 3 types of row operations that we're allowed to do, I'm telling you now, it turns out that only 2 of them are really necessary if row echelon form is your goal. And row echelon form is our goal right now because that gets us the triangular form. So that's pretty cool, right? But it means that we need to possibly add multiples of rows to another, and it means we need to possibly interchange rows. In some matrices, you would need to interchange rows. Now, our answer was, we wound up multiplying the diagonal entries, and another way that you can think of that was that it was the product of the pivots in B. Right, look at the reduced form. We multiplied the 1, 3, -4, -1. Those were all pivots of B, pivot entries. In general, I'm telling you now that the determinant of A is going to be plus or minus the product of pivots in B. And you might be saying, like, wait a second, how can it be plus or minus? Every matrix is supposed to only have one determinant. Am I saying that it has two? No, I'm saying that it's either plus or minus, where the plus or minus depends on how many row interchanges we did. You see why I'm saying that? See Theorem 3, Part B. We just wrote it above. It's on the previous page. When you interchange rows, it flips the sign of the determinant from, plus to minus or minus to plus. So if you interchange rows 0 times, then you just get what we got. If you had to interchange rows once, then I guess you're going to have a minus sign. If you interchange rows twice, you have negative of a negative, so it goes back to being positive. What if you interchange rows 6 times? You flip the sign, negative, positive, negative, positive, negative, positive, and you're back to positive. So it seems like it depends on whether the number of row interchanges is even or odd. Whether you're going to get positive or negative. So let's put some of these remarks together into an overall result. The determinant of A equals, where A is a square matrix. Now this is kind of going to build on what we said above, but it's also kind of new. I'm going to write this as a piecewise function and say there are two possible outcomes. We could get -1 to the r times the product of pivots in B. And I'm going to say this happens when A is invertible. Underneath, I'm going to say where R equals the number of, you know what I'm going to say here. You know what I'm going to say here, right? The number of row interchanges. Was it even? Was it odd? That's what's going to make this a -1 or a +1. What's the other case? What's the other case? Well, what if A is not invertible? The determinant of A is going to be 0. I'm going to put a big box around this. It seems important because it puts together a lot of what we've said. And of course, I have some things to say about this result. One thing that I want to point out to you is that I want you to notice that this, if you call this a formula, I want you to notice that it says the product of the pivots in B, not the product of the pivots in A. All right, so B is the reduced matrix. I guess I should call it the row echelon form matrix, right? You take the pivots from the row echelon form, multiply them together because that was a triangular matrix, and then you figure out, do I need a negative one out front or a positive one out front? And it depends on how many row interchanges happened. Also, for computing determinants, this is a method that computers often use because computers are very good at doing row reduction. You could just think of row reduction as like an algorithm that a computer can knock that out without any problem. You could give a computer like a really large matrix, and the computer can do row reduction, get it into row echelon form, and compute the determinant by doing this. It would keep track of how many row interchanges were performed. But you could also use this formula by hand, right? And I think that this is especially useful for large matrices, like 10 by 10. Last time in the previous video, we already did some determinants of like 4 by 4. But what if you had to do something that was 10 by 10? The row reduction might be a pain, but this would work. There's a little bit more we need to discuss. What's going on with the 0? Determinant of A is 0 when A is not invertible. Let's talk about that. Why determinant of A equals 0 when A is not invertible? That might be something that we said for 2 by 2 matrices, but why is this true in general for n by n cases? Well, think about the invertible matrix theorem. Is there something in there that we could use? The invertible matrix theorem says A is not invertible if and only if. Do you see what I'm doing here? Property 1 or property A of the IMT says A is invertible. I'm using the negation of one of the properties from the IMT, and it's going to be if and only if the negation of one of the other properties. A does not have a pivot in every row. Okay, so just to be clear, the IMT says if A is invertible, or rather it says A is invertible if and only if there is a pivot in every row. I did the negation of that. I said A is not invertible if and only if A does not have a pivot in every row. Okay? Well, if A does not have a pivot in every row, this is true if and only if B has a 0 on its diagonal. So what's going to happen when I try to apply theorem 2? I'm going to multiply all of the entries on the main diagonal, but one of them is going to be a 0, or maybe 2 of them are going to be zeros. And that's why the determinant is going to wind up being 0. I'll show you an example of this. Let's do a 3 by 3 example. Consider this matrix: 5, 1, 2, 0, 2, 4, 0, 3, 6. Before I even do any kind of row reduction, or before we try to apply like these results, can I just say that I think we could look at this And I think just by observation, we could tell that this matrix is not invertible. How do I know that? Without computing the determinant, how can you tell that this is not invertible? We know this is not invertible because something about column 2 and column 3. The columns are not linearly independent. I'm going to put this all in parentheses. That's just kind of an observation. Column 3 is a multiple of column 2. Or really, I could say column 3 is a linear combination of the other columns. So the columns are not linearly independent, so the matrix is not invertible. But let's say we wanted to use row reduction and get this into row echelon form. I guess I would want to get rid of the 3 down there. So we could do this in one step. How do you get rid of that 3 in one row reduction step? Add negative 3/2 row 2 to row 3. I mean, we don't have to do it in one step, but I just thought might as well do it in one step. So row 1 doesn't change, row 2 doesn't change. We get 0, 0, and then what are we adding here? Negative 3/2 times 4 is going to be negative 6. That's going to get us a 0 here. Now, this is in row echelon form. So by theorem 2, we should look at the pivots and multiply them. And we could say, by theorem 2, the determinant of A, I guess I didn't really call this original matrix A, did I? Well, I'll call it A now. The original matrix was A. The determinant is 5 times 2 times 0, which is 0. So, let me talk about this for a sec. We're gonna say this in a theorem in just a moment. We're building towards a theorem 4. But what's the point of all this? The point is, when A is not invertible, its reduced form does not have a pivot in every row. This means when we get it into triangular form, at least one of the diagonal entries will be 0. I could have circled the 0 if I wanted, but it's not a pivot. So I didn't circle it, but we were doing this. Here, I'll circle it this way. We were multiplying everything on the main diagonal. Okay, so when we get it in triangular form, at least one of the diagonal entries will be a 0. Then the product of the diagonal entries will be 0. So not invertible leads to determinant equals 0. Then the natural question is, does it also work the other way around? If the determinant is 0, does that mean it's not invertible? Is this if and only if? And that's what theorem 4 is going to answer for us. Theorem 4, a square matrix A is invertible if and only if its determinant is non-zero. If that looks familiar to you, it's because in an earlier section we said this for the 2x2 case. But now I'm telling you that this is true, and by the discussion that we've had above, it certainly seems to kind of follow from this discussion that This is true for the general square case. This theorem adds determinant of A is not equal to 0 to the invertible matrix theorem. The IMT. You know that we have so many statements on that IMT printout. The following statements are equivalent. We're going through all the letters of the alphabet. And I'm going to say soon, probably in about a week, we're going to actually add this in. Soon we'll add it as statement T. And we're actually skipping statement S for now. We're going to discuss statement S in about a week. And then we will add both of them, statement S and statement T, and we will have sort of the finished version of the invertible matrix theorem at that point. So theorem 4 is a big deal. It's great because it means if I give you a matrix and I ask you, is it invertible? You don't necessarily have to go through the process of trying to find the inverse. Like, we had a whole process of like finding an inverse of a 3x3 matrix. It takes a bunch of steps. But sometimes it's quicker to just calculate the determinant and figure out whether it's 0 or not, and that will answer yes or no. Is the matrix invertible? There's a corollary to this. Corollary to theorem 4. The determinant of A is 0 whenever the columns of A are linearly dependent. That's kind of what happened in the above example. I gave us a matrix A. I said it looked like the columns were not linearly independent. The determinant of A wound up being 0. So now we're just kind of formalizing that and saying it as a corollary to theorem 4. And one more corollary. The determinant of A equals 0 whenever the rows of A are linearly dependent. Now, that's something that we usually don't think about, right? We usually think about column vectors. We usually think about column vectors, and you could have a set of all the column vectors and talk about whether that set is linearly independent or dependent. But now I'm talking about the rows. That seems a little different. Let's prove these. Let's prove the corollaries, okay? So proof of 1. And I'm going to write these as short, simple proofs. These might be a little bit less formal than a textbook proof. I just want to give us a sketch of the proof or a rough idea. So, I hope you don't mind if I'm not going to write these in complete sentences. All right, just for the sake of time, we could say columns are linearly dependent if and only if E of the IMT is false, if and only if T of the IMT is false. So what's statement T of the IMT? It's this. It's what we just added. So the proof that we just wrote there, it's basically following from the discussion that we've had so far. If the columns are linearly dependent, you have one thing that's false in the IMT, Therefore, everything is false in the IMT, and this is part of it now. So that's the proof of 1. The proof of corollary 2. This one's more interesting because you might say, like, how are we going to talk about the rows being linearly dependent or not? Well, the rows of A are linearly dependent if and only if. You know how I said that we usually think of things in terms of columns? How about this? The columns of A transpose are linearly dependent. So you see what I did? I took a question about rows and I turned it into a question about columns. But instead of talking about the original matrix A, we're now looking at the columns of A transpose. The columns of A transpose are the rows of A. So this is a clever little trick. And this is true if and only if A transpose is not invertible. By applying statement E of the IMT. So the columns of A transpose are linearly dependent if and only if A transpose is not invertible. And this means that statement T of the IMT is false, since statement L of the IMT is false. All right, so we'll say that's a proof of the corollary 1 and 2. We've been doing a lot of theorems and discussion and remarks. Let's do a problem. I'll give you a problem to try. Let's do something that's just some concrete problems with some actual numbers in them. So example, which of these matrices are invertible? Now, remember, if it says which of them are invertible, it doesn't necessarily mean that you have to find the inverses. It's like a yes or no question, right? You don't have to find the inverse necessarily. Explain why. You could briefly explain why. We don't need a paragraph. Sometimes just a few words or a sentence would be good. All right, I'm going to write 4 matrices, and I'm going to give you some, chance to think about them. So wait till I write all 4. And there might be more than one method to reach your conclusions, but you can use some of the things that we talked about today. And you can probably use some of the things that we've talked about previously. I said there were going to be 4 of them, so let's make some room. And your goal should be to use theorems and statements as shortcuts wherever possible. All right, so I'd like you to pause the video and see what you can come up with for these. All right, so we've checked to see which of these matrices are invertible, and I'm going to go through the answers. I found that this one is invertible. I did not find the inverse of it, but I know it exists. And my explanation is because the determinant, we'll call it A. It's okay to call it A. It's 24, which is not 0. I'll say by theorem 2. Can I zoom in on this maybe? Yeah, let's do that. One times 4 times 6 is 24. And I'm allowed to do that because I see that this is a triangular matrix. So there we go. Determinant is non-zero. Next one I said is not invertible. There might be more than one way to see this, but I'll tell you how I saw it. I'm going to say because the determinant of A equals 0 by corollary 2. Since row 3 is a multiple of row 1. So if you saw this in a different way, that's okay, but I used this corollary as a little shortcut. The corollary says the determinant of A is 0 whenever the rows of A are linearly dependent, and I saw that row 3 is a multiple of row 1. I mean, we could say that row 3 is a linear combination of the other rows. So, yeah. Linearly dependent means determinant is 0. Determinant is 0 means not invertible. For these ones, I said this is invertible. It's kind of like the first one, because the determinant is, what is the determinant here? Multiply the things along the main diagonal. 7 times 7 times 7. What does that get us? I'm going to tell you, it doesn't really matter what it gets us as long as you can tell that it's non-zero. It's not 0, right? What is it? 343, I think? Is that close? I think that's what it is, but it doesn't matter. It's not 0. So just say, once you get this far, you can tell it's non-zero. And again, I'll say by theorem 2. Next up, the last one I said is not invertible. The way that I saw this, I said because the determinant of A equals 0. Now, I think there's more than one way that you could tell that this determinant is 0. But the way that I wrote it, I wanted to use something from today. So I said by corollary 1. By corollary 1, since a set of vectors containing the 0 vector is always linearly dependent. Do you see how that uses corollary 1? And it uses a fact that we had a while back, that if you look at these as column vectors and you say, wait a second, one of them is the 0 vector, so the whole thing is linearly dependent. Linearly dependent means determinant is 0. Determinant is 0 means not invertible. But there are other ways that you could have done this also. You could have used what we learned in the previous lesson, which says that you can find the determinant by doing cofactor expansion across any row or column of your choice, and we usually try to choose the one that has the most zeros. Well, if you try to find the determinant by using column 2, it's going to be 0 minus 0 plus 0, right? You're just going to get 0 anyway. So that's also a perfectly valid way to come to this conclusion. Now, this having a column of all zeros automatically tells us that it's not invertible. And I actually would like to take this and state this as a more general fact. If a square matrix A has a column of all zeros, or a row of all zeros, then the determinant of A must equal 0, and A is not invertible. Makes sense, right? And that's a nice shortcut if you're lucky enough to get a problem that has a row or a column of all zeros. Automatically know what the determinant is, and you automatically know it's not invertible. Now, this section is called Properties of Determinants, and we've spent most of our time talking about how row reduction affects determinants, and, Theorem 4 is a big deal, but there's still some other things we need to talk about. Other properties, other questions that need answers. So here are some questions. In general, I'm going to ask 3 questions, and we will answer these together. Does the determinant of A plus B equal the determinant of A plus the determinant of B? We'll figure that out. We'll get to an answer for that. Does the determinant of K times A equal K times the determinant of A? Like, are we allowed to pull a constant out? Question mark. And part 3, does the determinant of A times B equal the determinant of A times the determinant of B? Assuming that these are all square matrices of the same size and all of that. So what we'll do is we will answer these, but we'll start by checking these properties for the 2 by 2 case. Now, I want to be clear about something. You already know this, but I'm going to say it anyway. If we prove one of these properties for the 2 by 2 case, that does not necessarily prove that it always works for the n by n case. Right? Proving 2 by 2 is not the same as proving n by n. But I think that, what we're trying to do is we're trying to convince ourselves of whether or not these are true. This might give us some inclination of whether it's a yes or whether it's a no. Also, if we check one of these properties for the 2 by 2 case and the answer is no, well, then we can say that it's not true in general, because in general would be all square matrices. So let's check the 2 by 2 case, and maybe we find like a counterexample to make one of them might be a no. So let's start with the first question. This is kind of going to be like what we did earlier with 2 by 2 cases, where I have like a general 2 by 2 matrix. So let's check question 1. And we will let A equal the matrix A, B, C, D. We also need another matrix, so we'll let this one be E, F, G, H. So what are the determinants? Let's use the vertical bar notation. AD minus BC. And the determinant of this is EH minus FG. We're going to look at the question, the alleged equation in question 1. So the right-hand side of equation 1 would say determinant of A plus B So add these together and then find the determinant. It's going to be... oh, actually, sorry, I pointed to the left-hand side. Right-hand side is this, determinant of A plus determinant of B. So you just take this plus this. So it's AD minus BC plus EH minus FG. That's kind of the easy side. Now let's check the left-hand side. We want to see if the left-hand side and right-hand side are equal to each other. So the determinant of A plus B would be the determinant of, just add corresponding entries, right? All right. Do you think we're going to get the same thing? I would say at this point it's too early to tell, so let's keep going. This is A plus E, D plus H, minus B plus F, C plus G. And now I think we should distribute and see if there are any terms that cancel out or if there are any terms that we can combine. So the first part here is AD plus AH plus DE plus EH. And the second part is BC plus BG plus CF plus FG. Now, do any of these things cancel out? Doesn't look like it. Looks like we're stuck with all 8 terms. Well, this thing has all 8 terms. This thing had 4 terms. I'm going to say that these are not equal. So in general, statement 1 is false. So the answer to question 1 is, in general, no. Is it possible that you might find some matrix A and some matrix B where it works? Yeah, you might be able to construct a matrix A and B like that on purpose, but in general, dealing with most matrices 99% of the time, the answer is going to be no. So in general, the answer is no. Let's move on to question 2. I'd like you to try this one. I'd like you to try answering for the 2x2 case. What is the answer to question 2? Yes or no? And you can pause the video here. All right, so for this one, we only need one matrix A, right? Let's let A equal A, B, C, D. Then Ka is this matrix, Ka, Kb, Kc, Kd. Square brackets because I'm not doing determinants yet. Now I'll do a determinant. The determinant of Ka is Ka, whoa, what's happening here? Ka times Kd minus Kb times Kc. We could probably write that a little bit nicer, but I just used the definition of the determinant for 2x2 cases. We could pull out K squared. K squared AD minus BC. What happens when we check this? This would be the right-hand side of statement 2. Well, that's K times AD minus BC. And it looks like, in general, these are not equal. It looks like it's only equal if K is 1. Well, but if you look back at the question, it makes sense that it would be true if K is 1. we were really interested in general, is it true for multiplying by a scalar? And it looks like other than 1, which is kind of trivial, these are not equal to each other. So we could say, in general, statement 2 is false. It actually looks like we could come up with a different result based on this. So I'm going to do this off to the side. We could come up with a different result. And I'm going to say this as a fact. It's probably somewhere in the book. In this section, I would imagine. If A is n by n, then the determinant of k times A, well, we found what it's not equal to. It's in general, it's not equal to pulling out the k. But look at what we got. We got k squared. It was like instead of pulling out k, it was like we pulled out a k squared. And this was for the 2 by 2 case. So it turns out that this is going to be k to the n. So that's a little side note, and we could prove that if we want. Maybe we'll come back and prove that later. But for now, I'm just telling you it as a fact. We still have question 3 to check. So far, question 1 was false. Question 2 was false. Let's check number 3. Again, I'd like you to pause the video and try this on your own, just for the 2 by 2 case. So I'm going to let A be a general matrix A, B, C, D. I'm going to let B be a general matrix E, F, G, H. And I'm going to look at the right-hand side of statement 3. It would be the determinant of A times the determinant of B, which we understand is AD minus BC times EH minus FG. And I'll go ahead and expand this all out. ADEH minus ADFG minus BCEH plus BCFG. Now we're going to be checking to see whether or not this equals the left-hand side of statement 3. Left-hand side says determinant of A times B. So the determinant of, we have to do a little bit of matrix multiplication here. Two by two. This is good practice for you to do a little 2 by 2 matrix multiplication. You should have gotten AE plus BG, AF plus BH, CE plus DG, CF plus DH. So let's figure out this determinant. I guess this is AE plus BG times CF plus DH minus sign AF plus BH CE plus DG. Does this equal what we found above for the right-hand side? Again, I think it's too early to tell. I think we need to distribute this, look to see if any terms are going to cancel or combine, and then we'll have a better idea. So this looks like AECF plus AEDH plus BGCF plus BGDH minus minus expanding out this other one. AFCE plus AFDG plus BHCE plus BHDG. Let's remember that there's this minus sign in the middle, though. Does anything cancel? Yes. Over here, I have AECF, and over here, I have AFCE. Those are the same thing. Cross them out, because it's positive and that's a minus. Anything else? Yes. BGDH is the same as BHDG, and this one is plus and this one is minus, so cross them out. What are we left with? 4 terms. The 4 terms that we're left with are ADEH plus BCFG. I'm writing the letters in alphabetical order now. Sometimes I do that, sometimes I don't, but this is kind of the end of this, so getting them into alphabetical order. BCEH. Does that equal what we wrote above? ADEH, BCFG, there it is, BCFG, minus ADFG, there's minus ADFG, minus BCEH, there's minus BCEH. Look at that. Look at that. The left-hand side does equal the right-hand side. So we proved this, at least for the 2x2 case. And, yeah, turns out that statement 3 is true in general, not just for the 2x2 case. So that was a couple of pages ago by now, so I'll just write it again. Determinant of A times B does equal the determinant of A times the determinant of B. And of those 3 questions, this was the only one that had an answer of yes. Oh, I guess I should say this actually has a name. Theorem 6. And it says determinant of A equal, it says this for any n by n matrices A and B. There we go, Theorem 6. We just proved it for 2x2, but it's true in general. Okay, so we're almost done here. What we just did finished up our discussion of those 3 questions. We had 3 properties that we were questioning, and it turned out that out of those 3, only this one was true in general. There's another property, which I'm just going to say as a fact because I don't think it's called a theorem, but if A is invertible, then the determinant of A inverse equals the reciprocal of the determinant of A. So that's pretty cool, taking the reciprocal. I mean, the determinant is just a number anyway. It says if A is invertible, so we know that the determinant is non-zero, so we're not dividing by 0 here. For the proof of this, I'm going to encourage you to try this on your own. I'm not going to discuss it right now. You could ask me about it if you want, but I'm going to tell you a hint is to use Theorem 6. Oh, and, you know, we want to prove this for the n by n case. So in the textbook that we're following along with, this is actually a recommended exercise, so I'm not going to give away the answer right now. Feel free to ask me at some point later if you'd like. And one more thing, I think we could probably fit this at the bottom of this page. Another fact. If A is n by n, the determinant of A transpose So, right above we had a fact about the determinant of A inverse, and now we have a fact about the determinant of A transpose. This actually equals just the determinant of A. So why is this true? I'll give you kind of a rough explanation. It's because Theorem 1 that was in the previous lesson, the previous video lesson, it said we can do cofactor expansion across any row or column and still get the same result. And, when you go from A to A transpose, you just switch rows and columns. So if we're allowed to do cofactor expansion across rows or columns, then it's going to get the same result. And I think that this could probably be called a corollary to Theorem 1, because I feel like it follows very quickly from Theorem 1 and from the definition of transpose. I'll tell you that we probably won't use this right now, but this might be useful later. In the textbook, it's useful in Chapter 5. All right, so these two facts were just a couple of last-minute properties about the determinant. All right, so that wraps up our lesson on properties of determinants. I think that this lesson and the previous one, they really go together as a pair. First, we learned about determinants, what they are, how to compute them. And then in this lesson, we learned some properties of them. And, a pretty important property that we're adding to the invertible matrix theorem about whether a determinant is zero or not, telling us whether a matrix is invertible or not. So that's pretty important. I'll tell you that if you're following along with the schedule, it looks like at this point in the course, we're skipping around to different chapters and different sections. So the next video that you see is going to jump to another topic. But all of these things are related. Some of them we'll see the connections right away, and some of them we'll see the connections a little bit later. But that's it for determinants for now. Okay, so everybody take care, and I'll see you next time.